section 16.7 is about the divergence theorem. So that's going to be about the relationship between a three-dimensional region E and its boundary surface S. Okay. So just as some examples, I could have E being the solid sphere. So that would be this sphere together with all of the space that's inside of it. Then S would be its boundary surface. So that would just be the two-dimensional surface of the sphere. Okay. I could have a rectangular box, kind of like this book here. Okay. The entire rectangular box would be my region E. The boundary surface would actually consist of 6 different parts. There would be the top portion of a plane, the bottom, the front, the back, the left, and the right. So there would be 6 portions of plane that would be the boundary surface for a rectangular box. Now, not all surfaces are boundaries of solids. The surface has to completely enclose the solid. So if I have something like a portion of a paraboloid, that's open-ended. That doesn't completely enclose anything. Now, if I were to put a disc on the top to cap this off, then I would have a piecewise smooth boundary of the solid that's contained inside of that. Okay. So we're looking at regions in 3 space that are completely surrounded by some boundary surface. We're choosing to let E be what we call a simple solid region. Okay. That's basically just saying it's a sufficiently nice region. It's not super messed up. More technically, that means that it's simultaneously a simple XY solid, a simple YZ solid, and a simple XZ solid. Simple XY solid means that the top and bottom surfaces are continuous, that Z is a continuous function of X and Y, and that if I project onto the XY plane, I get a type 1 or a type 2 region. And then to be a simple solid region, that has to be true whether you sort of single out the top and bottom surface or the left and right or the front and back. Okay. S is going to be its boundary surface. S has to completely enclose the region E. It's got to be piecewise smooth, so it's okay if it's 6 portions of plane that are bounding a rectangular box, or if it's just one surface of a sphere that's enclosing the solid sphere. Okay. And it has to be oriented out, so away from the enclosed solid. Okay. Then we're going to have a vector field, and the rule is our vector field has to have continuous first partials, and that has to be true on some open region containing E. Now, a lot of this is just what I call niceness conditions, okay? That the region has to be sufficiently nice. So the surface has to be sufficiently nice. It has to be piecewise smooth. The vector field has to be sufficiently nice. It has to have continuous first partials. Those are important criteria. It's not super important that you have them all memorized, okay? So if I ask you to state the divergence theorem, and I might, I would say, state the divergence theorem, supposing that things are sufficiently nice. So I'm not looking for all of those details. What I am looking for is the relationship between the solid and the surface. That the surface is the boundary of the solid and that it is oriented out. And then what the divergence theorem says is that we could evaluate this integral, which we should recognize, that's a flux integral. So we should be able to calculate the flux of F across S, which is just this double integral, this surface integral. If we want, instead, we can calculate it as a triple integral of the divergence of F over the solid that's enclosed. So those 2 integrals will give the same value. Now you might look at that and say, well, but why would I want to do that? Why would I want to do a triple integral when I could just do a double integral? Because isn't that more work? And the answer is sometimes the double integral is simpler to evaluate, and that's what you want to go with. But sometimes the triple integral does actually provide a nice shortcut. So let me give you an example. Let's suppose that E is 0, 1, cross 0, 1, cross 0, 1. So just the unit box located in the first quadrant. So we come out to 1 in each of these planes. there. There we go. Lovely unit box is sitting in the first octant, okay? Now, its boundary surface is actually 6 surfaces because I've got the top, I've got the bottom, I've got the left, I've got the right, I've got the front, I've got the back. So if I wanted to evaluate a flux integral across the boundary surface, I'd actually have to do 6 double integrals. Okay, so S is its boundary. And let's say oriented out. I could do 6 surface integrals, but I could just do 1 triple integral. So let's say that F is xy, yz, xz, and I want to calculate the flux, which would just be this surface integral. As I said, that would actually be 6 surface integrals. Well, according to the divergence theorem, I could just do the triple integral over E of the divergence of F with respect to V. So, let's calculate the divergence. So remember, the divergence of F is just the del operator dotted with F. So that's the partial with respect to X operator, partial with respect to Y operator, partial with respect to Z operator, dotted with here xy, yz, xz. And of course we can't literally multiply these operators by these functions, but we can apply these operators to these functions, and that's how we interpret that. So this is the partial with respect to x of xy, plus the partial with respect to y of yz, plus the partial with respect to z of xz. So that's just going to be y plus z plus x. So we get y here, z, and then x. Okay, so that's my divergence. And because this was just the unit box, now I'm just integrating from 0 to 1, from 0 to 1, from 0 to 1. I'm going to just write this in alphabetical order. X plus y plus z, dz, dy, dx. Any order is fine because my limits of integration are all constant and they're all the same. All right, so that's the integral from 0 to 1. From 0 to 1, we're going to get xz plus yz plus z squared over 2. And that's evaluated between 1 and 0. And then we'll still have to integrate with respect to y and then with respect to x. Okay, so that's the integral from 0 to 1, integral from 0 to 1. When I plug in 1, I'm just going to get x plus y plus a half, minus when I plug in 0, everything's just going to go to 0. And then we'll integrate that dy dx. So that's going to give me the integral from 0 to 1. We'll get xy plus y squared over 2 plus 1/2 y. And that's evaluated between 1 and 0. And then we still have to integrate with respect to x. So we get the integral from 0 to 1. When I plug in 1 for y, I'm going to get x plus a half plus a half. So that's going to become just x plus 1. When I plug in 0, all of these terms will go to 0. Oops, minus 0. And so then we integrate with respect to x. So I'm going to get x squared over 2 plus x, evaluated between 1 and 0. So that's 1/2 plus 1 minus 0. We get 3/2. Wasn't super fast, but it was a lot faster than doing 6 different surface integrals. So sometimes, especially when the boundary surface is piecewise smooth, rather than just being one smooth surface, it can be advantageous to use the divergence theorem. Okay. So what we're going to do is we've stated it, we did one example, we're going to do a few more examples just so we get some practice using it. And then we're going to take a look at what does it actually tell us about what the divergence means. Because right now, divergence is just sort of this del dotted with F. It's just this manipulation of symbols. Why are we using it? Why is it useful? And what does it mean? We'll eventually be able to answer that. But I want to spend just a little bit of time just getting used to how the theorem works before we do that.